All right, so now that we've talked about mass action expressions, we're actually going to use that information to get what we call the chemical stability domains. And so these are the regions of pressure in which a material is quote unquote stable. So if we consider the iron oxide system, right? So I mentioned that there was these other oxides, not just FeO, but there's multiple. So we can have iron, we could have iron oxide, but then we could also have the other ones that we didn't talk about. We could have Fe3o4. We could also have Fe2O3. And so all of these would be stable at particular oxygen partial pressures. And so we're going to use these mass action expressions to see if we can develop a thermodynamic equation, or using those to determine which partial pressures would iron be stable: FeO, Fe3O4, and Fe2O3. So that's what we mean by chemical stability domains. What region of oxygen partial pressure is each one of those stable? And so we're going to start with the metallic version. So this was Fe plus 1/2 O2 goes to iron oxide. So we already kind of did this mass action expression, and we can write a formation reaction. So we know that this is actually the formation of FeO, and so we can look at the change in Gibbs free energy for that reaction. And we're going to look at those for the others as well. So I'm going to switch over to the slides, and I've got another quiz question related to this, and then we're going to work through the rest of the iron oxide system. All right, so that quiz question and what's going to help us start to talk about these chemical stability domains is what I want you to do is, using the expressions for Gibbs free energy and mass action that we've talked about, see if you can determine what oxygen partial pressure at which we have metallic iron in equilibrium with FeO, and then I'm going to give you that at a temperature of 1000 K. And so I'll also give you the free energies down here for various reactions that you might need. So see if you can do that, see how far you get, and then come back and we're going to work this one together, as well as look at the other ranges with the other oxides. All right, so let's start looking at this question of what partial pressure is iron and iron oxide, or we have it down here, at equilibrium. So we know that we have this information from the previous screen at 1000 degrees K to be minus 206.95, and that's in kilojoules per mole. So let's write our expression. So we know at equilibrium, the expression for free energy simplified to the reaction in its standard state is equal to minus RT natural log of the mass action expression, or equilibrium constant. And for this reaction, we solved it in the previous example to be 1 over PO2 to the 1/2. All right, so here we have, we can kind of just simplify this a little bit. Since the inside the log we have this on the bottom, we can just say log of PO2 to the 1/2 is equal to the negative, and so the negative would cancel out with this. So we just have RT natural log of PO2 to the 1/2. And we can also, what we want to try to do here is we're looking for its relationship with pressure. So we're trying to solve for pressure. And so what we can do is divide this and get that the natural log of PO2 to the 1/2 is equal to delta G FeO divided by RT. So we just rearranged it. And then we can, since this is a natural log, we can bring out the 1/2 to out front. So we got 1/2 natural log PO2. So basically just using log rules for that. And that gives us the same over here. And so we can multiply 2 on both sides. And basically now we have an expression for PO2 if we know the free energy and the temperature and then the gas constant. And so all we have to do is, if we want to get the PO2, is take the exponential of both sides, and then we'll have PO2. So this here is equal to minus 49.8 if you plug in the value from up here and the temperature. So it was we have this at 1000 K, and then the gas constant is R equals 8.314 joules per mole K. And so plugging that all in, we get this for the natural log of PO2. And so that would lead us to a PO2 of 2.4 times 10 to the minus 22 atmospheres. And again, inside the natural log, technically there's no units, because again, this is log PO2 over 1 atmosphere, because that's the relationship when we're talking about activities. And so that's why we can assign a unit of atmospheres to this. And so what this tells us is that at this pressure of oxygen, we have both iron and iron oxide, FeO, in equilibrium at this specific temperature, right? What that also means is that if we push this pressure in one direction or the other, we're going to favor one side or the other, right? More oxygen would push it towards FeO. So if we have a higher than this pressure at that temperature, we would drive the reaction towards FeO. And if we had a lower than this pressure, we would drive it towards this side, which would give us metallic iron. So that's kind of the importance of what this number is telling us in this example. So here in a second then, we're going to come back and look at the other chemical stability regions for the other oxides of iron and see if we can get a bit, sort of all of the chemical stability domains for this system. All right, so now let's consider the chemical stability of the next set. Sorry for the zoom again. So now let's look at between iron oxide, FeO, and then the next highest oxide, which would be Fe3o4. So let's look at the stability between these two. And so for this one, we're not going to look at the formation of this component, because we want to compare it to this oxide. And so we're going to write FeO, and then it's going to require more oxygen. So we're going to have O2, and that's going to lead us to Fe3o4, but we do need to balance this reaction. And so we've got 3 irons over here, so we need to balance this with 3 over here. Then that would give us 5 oxygens here and 4 over here. And so we need to take 1/2 of this to balance the chemical reaction. And so for this one, unlike our other one, where we had iron, metallic iron, and oxygen going to FeO, here we have oxygen, oxide to oxide. And so this isn't the formation reaction of Fe3o4 from iron and oxygen. It's from iron oxide. And so this reaction, so the Gibbs free energy for this reaction is actually the Gibbs free energy of Fe3o4 minus the Gibbs free energy of 3 times that of FeO. So if you go back to those definition, you can work that out, because again, these were the values for formation. And so if we're talking about oxide to oxide, then we have to adjust. And so we can do that by basically evaluating each reactions, formation reaction, and then subtracting. That's what it ends up being. But you might kind of work that out on the side and see if that makes sense to you, that this is Fe3O4 minus 3 times FeO. And so if we do that, then this is equal to minus 171.8 kilojoules per mole from the values of this and this that were given in the previous problem statement. Okay, so again, if this doesn't make sense, you might go back and just rework this, taking into account this formation reaction and this formation reaction, and you have to get it to look like this, and that's how you do it with this minus 3 times this. Okay, so the next step after we have this is we want to get the mass action expression, K equilibrium, and so we can write that as activity of Fe3O4 over activity of FeO to the 3. And then, again, I'll just make the direct substitution in for the pressure here. So again, we're dealing with two solids, and if we assume that they're pure, then both of these go to 1. And so we would just be left with 1 over PO2 to the 1/2, just like we were last time. And so if we do the same maneuvering with that equation, we can, again, do the same maneuvering as we did for the previous problem, and we'll end up with a similar expression. So I'm going to kind of skip the algebra rearrangement here, but if we just solve for log PO2, we'll get 2 times the Gibbs free energy of that reaction over RT. And so we have the value of that we got up here. And then we have, and again, this is in joules per mole K. So we will have to account for that up here. So this is in kilojoules. So we want to convert this into joules. So if we do all that, then what we get for PO2 is 1.14 times 10 to the minus 18 atmospheres. So this, again, is the equilibrium pressure at which iron oxide FeO and Fe3O4 are at equilibrium at the same temperature. Again, all of those were at 1000 K. So the equilibrium pressure at which, at that temperature, these are in equilibrium. So the same idea as before. This is a slightly higher pressure than the 10 to the minus 24 that you saw in the other case. So at this pressure, they're in equilibrium. And then if we go lower than this, we drive it towards this side. And if we go higher, we drive it towards this side. All right. So then now we're going to look at the last case of Fe3O4 to Fe2O3, and we're going to do it in the similar way that we did this one. All right, so now we're going to look at Fe3O4 to Fe2O3. And we're going to approach this in the same way we did the last part. We first write out the expression. I'll go ahead and add that later. And we know it's going to take more oxygen because it's a higher oxide. And so again, we balance this reaction. So this is 2 here, 3 over here. So we need a 2/3 over here. And then that leaves us with needing to balance the oxygen as well. And in this case, it's 1/6. And so if you're wondering why do it this way and not try to make them integers, it's because we want to keep this as 1, so that when we are dealing with the Gibbs free energies, it's in terms of moles of Fe2O3 and not one of these others. And so when we do that, our reaction for this would be Again, these are not the formation reactions. This is from Fe3o4. So we need to consider the formation reactions of each of these, which is what's given to us. And so that would be delta G Fe2O3 minus, then we have the 2/3 here. (3O4). So when we do that using the values that we had, that gives us minus 561.8 minus 2/3, and then that value is minus 792.6. And overall, when we plug those numbers in, we get minus 33.4 kilojoules per mole. So similar process that we did for the last one, accounting for the formation reaction. So these are the formation reactions. And then the same thing, we calculate the mass action expression, and just like we did before, we get 2O3. There's no coefficient, and then it's activity of Fe3O4, and then that's raised to the 2/3, and then we have PO2, but in this case it's to the 1/6. So that's the difference here. And then again, we're going to assume that these are pure solids, so this goes to 1 and this goes to 1 as well, and we're left with 1 over PO2 to the 1/6. And then we're going to algebraically work through the expression, right, of this. And if we rearrange that in this case, and again, I'm skipping some steps here, but you see that the natural log of PO2 is going to be equal to 6 times delta G of the reaction at equilibrium, at standard state, over RT. And then we plug in the value over here for the reaction, and then the temperature of 1,000, and then the gas constant. And all of that, we get PO2 to the 3 is equal to 3.4 times 10 to the minus 11 atmospheres. So again, this is the pressure of oxygen at which both of these metal oxides are in equilibrium at 1,000 degrees K. And if we increase the pressure, we drive it towards this, and we decrease it, we drive it towards this side. That's what this is telling us. And so if we put all of this together and we look at those domains, what we'll see is that if we look at all of the different compounds that we've been looking at, iron, iron oxide, iron 3O4, iron 2O3, what we see is that this is iron is stable from basically 0, basically really low atmospheres, up to 2.4 times 10 to the minus 22 atmospheres. So that first number that we calculated. And then FeO is stable from that number of 2.4 times 10 to the minus 22 up to the next number that we calculated, 1.14 times 10 to the minus 18 atmospheres. And then this one is stable from that number up to the next one, which was 3.4 times 10 to the minus 11 atmospheres, which was the last one. And so this is Fe2O3 is stable above or equal to 3.4 times 10 to the minus 11 atmospheres. And all of this, again, for clarification, is at equilibrium at 1,000 K. So that's kind of the information that these chemical stability domains are giving us in terms of these pressures. So it tells us where each one is stable under these conditions, assuming that these are all pure compounds from these assumptions that we made over here.